our first speaker after the coffee break now will be Michael Flaxman, who is he has a natural history background because his BA is in biology, which is probably the only science background we'll see this morning, I guess, which is great. But further on, he did his master's in community and regional planning from the University of Oregon, and later on he did his PhD with Carl Steinitz at Harvard in geodesign and urban design.
Yep.
Something like that.
Well, it hadn't been invented yet, but that's part of the story.
Well, I'm looking very much forward. Actually, Mike jumped the fence. He used to be in academia, but then he decided to do something about it and actually work with the knowledge out in the industry, out in the communities, and therefore he founded his own company. I'm sure he will give us some background on that in a while, but he is actually very much at a point where knowledge is taken into action. So show us how it's done, Mike.
All right, thank you. I was realizing in Tom's presentation that I had a really great deal of historic luck in my career. I studied with Ian McHarg for the year that he was at the University of Oregon, which he did late career. And I also studied with Carl Steinitz at Harvard. But when I started this, our digital tools basically were command line and very non-graphical. And you were really happy if you could get a statistical plot or a grayscale map that looked horrible, and every cartographer would look down their nose at you for the maps we were producing. But we've really seen a huge growth in the digital capability, and then I think it's changing practice a lot. As Hans mentioned, I've gone back and forth between academia and private practice a couple of times now. I was the industry manager at ESRI, and basically was brought in by Jack Dangerman to do the technical lead for the Geodesign team. The original, the team started a year before the term was coined, and I was at the table when Jack and Jack coined the term. It started out as geospatial design, incidentally, and that was a mouthful. That was my term, and Jack brilliantly called it geodesign, and the world hasn't been the same since. So dropping a syllable really helps sometimes. The few things I wanted to talk to you about today are examples really of current practice and thinking. Wanted to give a quick tour through starting issues, but Tom covered some of that so well that I'll keep it quick. I'm going to talk about 3 different current projects, all in Florida, which is my favorite study site in the US. When I was at MIT, I was looking for a place that had rapid population growth, huge climate change, and lots of endangered species. And Florida's kept me busy for nearly 10 years now. Although I do also work in South Africa and a few other locations like Tahoe. So my little company is basically a 5-person shop at this point. We've got two developers and 2 planners, in addition to myself, and my wife runs the books, little family shop. We basically are concentrating on consulting and custom technology development for large, tough problems, basically, when we tend to get called in. A few of the current clients and sponsors include the National Science Foundation. I'll talk about a project that they've sponsored. The Florida Department of Environmental Protection, the USGS, and the, sorry for the European audience, so US Geological Survey, and NOAA is the National Oceans Administration in the US. So we've been doing mostly things with land use planning and land use, but also starting to apply some of these techniques first coastally and then actually into marine planning context. About 2007, when I graduated Harvard and was wondering why landscape architects weren't using a lot of the original ideas that I saw in Design with Nature to my satisfaction, I got it under my head that maybe it was at least partially related to tools and the awkwardness of current digital tools in expressing design concepts. That's really what led me to work for ESRI. And I came up with this preliminary definition, which Stephen then helped me craft and refine. But originally, I talked about geodesign as a design and planning method that tightly couples the creation of design proposals with impact simulations informed by geographic contexts. And that was very much a functional definition. It kind of allowed me to, for myself, say what did I consider geodesign, and if it didn't have a design proposal, which was my shortcut for a positive change, or it was forward-looking and was proactive, I wouldn't count it. And if it didn't include impact simulations that were serious about the geographic context in which the design was situated, that I would also dismiss it. So that was my two-part test early on. As revised with Stephen, a couple of refinements. So we said geodesign is a method which tightly couples the creation of proposals for change with impact simulations informed by geographic context and systems thinking, normally supported by digital technology. So a little bit more verbose. So those of you who know me or have seen my work, I'm a big advocate of rapid iteration. That's what I learned in design school. I was expecting to learn the magic secret to design, and I learned the creative process by which designers work. And so that influenced me a lot in terms of what I was pushing for in technology. And so in between these two definitions a few years apart, obviously the focus on the iteration of ideation and evaluation that Tom also talked about is central. The use of geographic context has also stayed and is still important. And the concept of supporting multiple evaluations and disciplines within some form of integrated system, I think, has always been key. And the question came up in the last session about spatial decision support tools. Well, some of those have had the same concepts technically as geodesign tools for many, many years. I tend to divvy them up depending on how focused they are on a single stovepipe versus how inclusive they are. So a forestry management tool that only gives you board feet of timber coming out, I wouldn't call a geodesign tool, even though, yes, it includes a lot of the elements. It has more to do with the concept of including other disciplines and other resource values, for example. So I think that the technology isn't so different. The application domain is different in that case. And then the changes in the definition that just noted, basically a big one has been a broader notion of proposals for change instead of design proposals. And that you could think of as entirely semantics, but it's actually trying to be more inclusive. It's one of the things I learned from Jack Dangerman and his campaign to popularize geodesign, that we really want to invite people who don't typically characterize their work as design with a capital D, and yet they do design, and we're all affected by it. And so just the recognition that talking about those things in terms of different scales, we have different nomenclature, I think has been a significant change. And the second addition that really came from Steve was to be explicit about systems thinking in addition to geographic context. So initially I'd thought geographic context kind of forced you into thinking about systems, but indeed it's not just about including geography beyond site scale, for example, if you're working on a site. It's actually about seeing how your design interventions or policy changes are affecting systems. And so those are kind of the starting basis of some of the ways that I'm now thinking about the problem as opposed to 5 or 10 years ago. So I want to show you 3 projects. The first of them is something known as the Beaches Habitat Conservation Plan, or HCP for short. This is about a 5-year study that's coming from a very classic regulatory perspective, the Endangered Species Act in the United States. So it is about as classical in terms of starting formulation as you could want or fear. But unlike the most famous part of the Endangered Species Act in the US, which is very preclusionary, the HCP is a mechanism under that law that explicitly permits forms of development and management, but it requires impact assessment. And so obviously that's more fun territory for me to play in. And so the basic idea is that you assess permit fees for activities that cause so-called incidental take, and that's the legal term. So accidental harm in the conduct of otherwise legal actions. And similar to the German planning context, there's a kind of hierarchy. So you're supposed to try and avoid impacts where possible, minimize them where it's not possible, and mitigate them where necessary. So you kind of start at local and you avoid as much as you can, then you work your way out to broader schemes. But there's explicit trading of habitat and habitat quality in these plans. This is the largest single HCP ever done in the United States. Typically, habitat conservation plans are done at a county scale or smaller, and usually for a single species. So the other thing that scared other people away and attracted me to this project was the scope. So it had 800 miles of beaches, so 1,600 kilometers of beaches. I didn't put the population there, but there's 16 million people currently in Florida. So you can put that in a local context. A lot of people, a lot of length of coastline. And coastline is, a geographically challenging thing because it's a very narrow strip of land across a huge area. So those of you thinking about and used to cartography realize that's a cartographic challenge, among other things. The plan overall was to cover 16 species, all of them endangered species, all of which could, in theory, block all development. But any of you who have been to Florida will realize that we haven't stopped development on Florida beaches. Quite the opposite. So lots and lots of people conflicting with lots and lots of species. The species considered include sea turtles, shorebirds, seabirds, and beach mice, several species of each. We've got 5 different species of sea turtles, for instance. And the reason I was brought on board is they tried it once without me and got slapped down in a sense because they neglected climate change. So they went back to the drawing board, got their teeth kicked in, and went back to the drawing board and called me up because I had done a lot of work on climate change planning and how to bring that into decision process. So the approach in this one conceptually has basically been to distinguish 2 different types of scenarios, and this is something that is not in Carl's framework. It's kind of an addition to it, but I use it fairly frequently. And it helps in dealing, I think, with this mishmash of design and large-scale landscape planning. So we're explicit about distinguishing exogenous scenarios, which is the $10 word, or context scenarios, which is the $1 word, where we consider climate change, population change, land use change, basically things that are really important to your phenomena that you're interested in, but they're beyond the control of the plan. So the Florida beaches HCP can't control how many people move to Florida, what global climate happens, or how land use policy is done in Florida. But all 3 of those things are vital to a successful plan. So we bunch them up into a set of exogenous drivers. And then we also are very careful to make sure that we have plan and policy scenarios, that we're really explicit about what the plan can do. And in this case, we have kind of 3 dimensions that the plan can take on. So the plan basically defines incidental take. So when is a species harmed or harassed by human activity? So we have to define that. It defines minimization and best management practices rules. Sorry for the English acronym there. And it defines mitigation funding and actions. So all 3 of those are kind of the dimensions of action in this context, but it's a very broad scale notion. We're not doing design of individual buildings or even development districts. The technical challenges in doing this I thought were quite interesting. The first one I realized even in driving around the state for all the initial meetings was that it's roughly 400 miles from one end of Florida to the other. And so that wasn't a problem just for me as a consultant, which it was, but also that the species and local conditions expertise was all over the state. So you'd ask a sea turtle biologist in the southeast about sea turtles in general, and you'd get a very specific local answer. Well, here they do this. And you'd ask on the other side of the state and you'd get the opposite answer. And so that got me thinking, well, you know, even though it's a statewide project, really we need some kind of web-based technology, because we just can't get all these people reliably into one room, one place, and one time. It also turned out that most of the people with the deepest expertise lacked either GIS access or staffing to support them on that. And that was particularly true of the biologists, but also a lot of the state permitting folks. And I already mentioned conventional mapping on paper. We tried it a little bit, and it was just using way too much paper, because to get 800 miles of coastline onto a map at a sensible scale and to be able to talk about details is too hard. So that made me want to go interactive with this, basically. So the solution that we came up with was to develop an online impact assessment framework, which pre-ISIS we called ISAIS. I may have to change that name, but basically we said, well, what's so hard about impact assessment? You know, we've all done spatial overlay for years and years. Let's just put that part on the web and allow the managers and biologists to look at various scenarios and compute, twiddle with impact parameters and look at results interactively. And so we did that kind of basic form of overlay in an online format, which I'll show you in a second. And then we also found really quickly that we needed to be able to do a vast number of custom reports. And so rather than to tear our hair out and become the GIS service bureau for the state, and by the way, there are about 100 people involved in terms of experts on this project. So 20 people regularly meeting and about 80 involved as species experts. So rather than become their GIS service bureau, we had great incentive to step out of that and let them do their own custom reporting. And so one of the things that I haven't found in a lot of online tools, and we've pushed on quite a bit, is just the ability to summarize by arbitrary political or management regions on the fly. So those of you that know ArcGIS, that would be, you know, region statistics, basically, but done on the fly. So the county person can get their county, the water management district person can get their water management district, and the statewide politician can get a statewide number, et cetera. So just abstracting that out so people can pull from GIS dynamic reports. So a few different pieces to this. We had to simulate future development permits. And I'll skip over the details, but effectively we had relatively poor data in terms of spatial data. We had points for permits, and the points weren't accurate enough to position on a parcel, not to mention where on the parcel. They were done pre-GIS. So the benefit was that we had 30 years of full permit data, and the frustration was they had never used GPS or heard of it. So we had to develop a strategy based on poor spatial data at a fine scale, but actually 30 years of permit history, which was quite useful. We simulated the direct footprint of development, but using points. And so as a simplification, because we didn't have polygons effectively, we measured the average footprint and setback from the mean high water line, sorry for the acronym. And so we basically did classic GIS overlay, nothing particularly innovative except doing this online with 100 people using it. And we also had a very simple model for indirect impacts initially. And we said, well, look, there's points, and we're going to do circular buffers. We're not going to do cost distance or fancier stuff, because we need this to work at scale for lots of people. And so you basically say, well, you can simulate indirect impact as a fall-off curve. And the chart on the right shows beach access to shoreline recreation sites by foot traffic. So, you know, if pedestrian trampling of seabird nest is an issue, which it is, and you need to know what happens when you put a new beach access site, it's a very simple model, but for this big a statewide project, we needed a lot of very simple models. And actually, we took this data originally from Australia. I know there's some people around that could help us to do a better job with this with some Wi-Fi and other new technology. But Florida currently has no direct measurements of where people are on the beaches. So need to scope a nice study. Those of you that want to do a study of beach use in Florida, that's probably a good winter study for around here. So the online interface looks something like this. Can you all hear me if I stand over here? Yeah. So basically, and sorry to do this interactive demo, not interactively, but we've got a set of scenarios, about 12 in here. So this is a minimized scenario, for instance. Set of time steps, all of our 16 species, and the various permit activities. And these effectively are all toggles interactively. So you can switch between scenarios and turn off which species you're concerned about and which activities you're concerned about. And the system does an interactive aggregation on the fly. So for example, at the statewide level, here is the take for all of the species and all of the activities. And you see that Sarasota County is the highest. And it's going to lose 1,100 and such acres of habitat in the simulated future, which is actually a 25-year simulated future, and what fraction of the habitat in that county. So very simple formulation. It supports huge scale differences, and so here's a jump from the state down to the beach, and these are now approximately 100-meter wide sections of beach, and the various direct activities that are causing impacts on the beach. So the same idea, summarizing spatial overlay buffers as it's been done in GIS for years, but done dynamically on beach segments. So as you zoom in, you're getting summaries on the fly of different units. So the same interface applies in terms of species and activities, but obviously you can drill down and figure out, is it single family residential or commercial that's causing the most impact, and where. And if you want, you can go to the individual kind of point and buffer level and pull those things apart and look at where particular pieces of habitat are being affected. So that's kind of the mechanism underneath the scenes. But in practice, since we observe people using this, most people are actually using the higher levels aggregation all the time. And then they'll drill down to this detail level, and they'll find errors like this simulated point on the bridge. So it's useful to have the detailed drill down and kind of the full detailed impact model. But actually, our experience is a lot of people are more interested at the summary level, making sure they understand the overview patterns. And I mentioned it does reporting on the fly. So here's one example of the on-the-fly reporting. This is a classic bar chart. The only difference is that this is interactive. So as you pan and zoom around the map, you get a live readout of what's causing the incidental take in that location. And you can zoom out and do this for the whole state. So again, it's really not rocket science. For any of you that have done GIS, this kind of stuff has been done on the desktop for many, many years. We're just bringing it to a much larger audience by not requiring any GIS software. This is just a web page that people can go visit. The stuff that we're just getting into doing now, I thought I'd kind of bring up this is midstream in a large process. We're struggling with the 3D side of this, and so I was going to show you one of the main 3D issues, and that is lighting. So sea turtles, I don't know if any of you know sea turtle biology, but when the little hatchlings emerge, they go towards the brightest light. And historically, the brightest light used to be the moon shining on the beach. These days in Florida, it's usually the casino somebody put on the beach. So they go the wrong direction. And that's a problem, and it's a hard problem. It turns out that there are different frequencies of light that they're more or less sensitive to, and if you go to this amber kind of lighting, you can basically not trip and fall, but still be safe for sea turtles. And so during the nesting season, there are a number of counties in Florida that require this kind of lighting. And one of the questions for the policy side of the program is, do we require this all over? And this is just an example of some of the minimization work that's been done. So you have a place that had just glaring lights out onto the beach, and then it gets basically lighting design retrofits, which those of you in Europe and in Denmark in particular, I have to say you're very spoiled. You have really good lighting design here. In the US, we tend to have a lot of this floodlight stuff. It's harsh, wasteful of all things, resources, and horrible design. But it's very difficult to move forward from. There's a lot of safety regulations that are just based on foot candles of light hitting a stairway, treadwell, and so forth. And most of the regulatory environment is just encouraging engineers to pour more light onto stuff. You'll never get sued if you put too much light. So that's how the current legal system works. There is good scientific evidence that if you do this kind of lighting minimization, you have very positive impacts on the sea turtle. So these are the number of hatchlings that are disoriented, so they go towards the casino instead of towards the water. And if, there's some noise in this data and it's early data, but basically you can drive that to 0 if you solve the lighting problems. So in Tom's example, scientifically this is solved, right? We can go home now. Well, problem is we've got 16 million people using Florida's beaches. Actually, 16 million people living there, another 20 million visiting and using the beaches. It is a little harder to solve in practice. What we're starting to experiment with, you're probably familiar with it over here as well, is the use of LiDAR data. Light detection and ranging, or 3D point data, is available for the state of Florida for all of the coastal areas. And in section, you can actually see fairly well the kind of quality of the data that you get. We have done just a preliminary study at this point to see a kind of feasibility test. So we gathered 264 photo points with GPS and Illumines data. Basically, you get an astronomical light meter that's sensitive to a very wide range of light and its frequency. And you collect a number of observations, basically physical observations on the beach. And you can then take the LiDAR data and classify it according to into buildings, terrain, and vegetation, and do, again, a very classical GIS technique, viewshed simulation. But the trick here is you got to do it at massive scale. And those of you that have ever done this on the desktop realize it's computationally intensive. So this is an example, just a test of building lights from the 17th floor and how those propagate out onto the beach through actual vegetation and through other buildings, or not through other buildings. So as obscured by a variety of built and natural environment. Oops. So in summary, the Beaches HCP project started with a classic endangered species impact assessment. That's what we were given up front. And we added a bunch of stuff along the way when they hired us. And we added this notion of contextual and policy scenarios. And we added online tools for 2D impact assessment. And we're now working on the 3D aspects of that. But I'll return to this theme later. It's when you have good clients that are willing to work with you, it's very rewarding because you can give them more than they ask for. And I certainly in this project, we keep giving them more than they ask for. And that seems to be an effective way to move things forward. So if I had waited for them to commission a LiDAR survey, it would have been a long time. Now, I took 2 people out on the beach and we did this lighting survey over 3 nights, and we came and presented them, and then they said it was a good idea. So, so we've been kind of educating the client about what's possible as a way of building ourselves a more interesting project. A much simpler project now to show quickly kind of the other end of the spectrum. So we're commissioned to do landscape conservation scenarios for the state of Florida. And this was a kind of rapid small budget project done within 6 months. the Peninsular Florida Landscape Conservation Collaborative, or PFLCC, has no good acronym. It's a real mouthful. But they're a federally funded initiative around the United States, and there are 30 or so of these. And they're designed to create public-private conservation partnerships. And they fund research a little bit, but they're currently focused really on the notion of what can we do with paid and voluntary conservation. So not traditional fee simple conservation, buying conservation lands, but paying farmers for water storage or paying them for species habitat or buying conservation easements. And those of you that are following the state of Florida politics at all will understand the reasons why the conservation community is thinking in these terms. So the key principles for this study were to make sure that it was stakeholder based, that we dealt with multiple dimensions on the planning scenarios, and we could simulate those with rule-based allocation and test strategies in spatial context. So in this particular case, we simplified some of the scenarios we'd done elsewhere in Florida, and in fact, relative to what I'll show you in a minute. But we said there's only one level of sea level rise. Oh, you can see it. My pointer isn't working now. And there's only one level of total population increase, which is roughly a doubling of Florida's population. And there's only one level of conservation resource, but you can choose to spend the money in 3 different ways. And actually more than 3 different ways. So you can choose in terms of the value of the land you buy, and you can choose in terms of the conservation strategy which you use. So the strategies range from 50% fee simple and 50% easement to 10% fee simple and 90% easement, for example. And this is a little bit of technical detail, but there are existing prioritizations for the state of how to spend the money, and we looked at alternative prioritizations as well. So we generated really quickly 3 different scenarios from these combinations of assumptions. And the 3 is not a magic number. It was just time and resources and scope for this particular project. They gave us time and resources to do 3, so they picked the 3. And we did a stakeholder-based process with this particular commission to figure out which 3 scenarios were the most important for them. And for example, we didn't look at variations in sea level rise in this study for that reason. We've looked at it elsewhere. So those assumptions become numbers, right? So through a kind of classic modeling approach, you parameterize a model based on these assumptions. But you talk about the assumptions first in qualitative terms, and then you scale those relative to actual practice. And in our case, I think it's really important for conservation. Development is usually planned this way, and people think about development program and the amount and number of people. People don't think about conservation this way, but there's a history of conservation, and you can see how much money was spent by whom and where in conservation. And in this case, it was very important to show people, well, if you keep spending at this level, here's what you're going to get in 50 years. And in the context of Florida, where you have a running battle with development, the fact that you've spent $300 million a year on conservation might sound good in the abstract, but when you're talking about 16 million new people moving to the state, you're losing the battle. So it's really important to scale these things and not just talk about conservation abstractly, but talk about conservation given actual units of cost and size. We did fairly conventional land use change modeling with a relatively high degree of articulation of classes of urban use. And the reason for that is that in Florida you have a very little bit of extremely high density development, i.e. Miami Beach, and you have huge parts of the state that are 5-acre residential lots. So any average you could pull between those would be horrible. So we were really dealing with a very large state with very large variation in land use practices that forced us to be quite articulate. So instead of doing an urban growth model that was just one big blob category of urban, we really got particular about what is it that leads somebody to go move into rural Florida and live on a ranch that's 5 acres. It's they call them ranches. They aren't really ranches, right? Because you can't ranch effectively. That's not an economic unit. But it's so in any case, we're very interested in what led people to live in these different locations at these different densities. And just a couple of examples. Again, we did this in the form of an online interactive website, so you could zoom in and basically look at land use change in comparison between scenarios around the state. And these are, sorry for the lack of legend here, but basically, as you'd expect, the green tones are different kinds of conservation, and the oranges are different kinds of development. And you can see that there are very large potential differences between the conservation practices. And that's what this particular group needed to focus on. So, in conclusions, this one was a quick study, and we used existing scenarios and basically simplified them to play out what the client needed in terms of decision and choice. So effectively, we just played with the amount of conservation and the rules for conservation. Everything else came from other studies and prior scenario work. And that proved to be very effective for this group of people. They had a small budget and a small period of time, and they needed to make a decision. Were they going to spend money on buying land, or they're going to spend money working with farmers to buy easements? And this is kind of directed at a narrower policy question, but I should have mentioned up front, I mean, it's a very important question in the politics of Florida right now, because the state is very, very conservative, and they are not having an easy time doing government acquisition of conservation lands. So it's a big strategic choice, and it's quite hard to do individual negotiation with thousands of farmers, right? So if they're going to go that direction, they need to understand the scale and the magnitude of the endeavor. Sounds easy in theory, and then you start looking in practice, it's really quite complex. All right, so the third project I wanted to show, basically this one is earlier in development, so a little less graphical, with apologies, but the National Science Foundation has been kind enough to support my work. And the purpose here is basically to develop new science and methods to assess water management options for South Florida under climate change. So again, with Florida, but this time on the water side. So we started out thinking about development, then we thought about conservation, now we're thinking about water. The general methods here are to concentrate on ecosystem service quantification. And I should mention I'm one of a team of 15 people working on this, and most of them are natural resource scientists. We've got Michael Mann doing the climate change planning, so the guy that did the original hockey stick graph, if any of you have seen that, had the misfortune of being right, but 30 years early. Anyway, he's on the team doing the regional climate downscaling, and we have a number of really excellent top league natural scientists on the fisheries side, for example, quantifying fisheries impacts. So our role within this huge model is basically strategic scenario planning, and it wouldn't surprise you to learn we're working on web-based APIs now for scenario development and sharing in the context of this project. And even though it's early, I think it's kind of an interesting one because it's so hard. So I'm going to show you not all our successes, but some of our challenges as well here. So we have the same kind of base online formulation of exposing scenarios as maps. We've got choices of scenarios. We've got time sliders. Sorry, this is a little off the scale. We've got the ability to show networks and aggregate. I'll show you the network in a second, but you can aggregate on the fly and figure out. Sorry, this got cut off, but for example, here the amount of future development of the type suburban in a given scenario. So for every county, if you're zoomed in at this or zoomed out at this broad scale, you can see the number of acres of projected suburban development or any other type. And new for me, I haven't done a lot of water management work in spatial scenario form. Each of these future scenarios has a hydrologic future. And the hydrologic future includes how you distribute water. And that distribution has a whole set of rules and infrastructure associated with it, of course. So effectively, this is the kind of deepest and toughest scenario project I've taken on, maybe because it's got 15 NSF scientists. And it's at risk of analysis paralysis. So my job is to try and avoid that. We'll see if I succeed. But effectively, we've got 6 different drivers of change in this. And 2 or 3 of them are new for us. But population growth, urban development patterns are pretty routine. In this particular study, we're looking at green infrastructure explicitly and directly because it's being quantified. And we're looking at payments for ecosystem services directly and quantitatively. So that's the advantage to having the big team. And we're using the two levels of hydrologic model, but the main one is an optimization model. And so if you tell it where the water should go, it will try to get the water there in a quasi-optimal fashion. And optimal, you have to think about that as occurring within a particular scenario, because optimal under current conditions may not be optimal in the future. But the starting pass on this is that by taking into account ecosystem services at all, we're changing the equation. Because right now in Florida, they're very explicit about planning for water demand and for avoiding flooding. And they're very implicit or tacit about natural resource benefits. So they plan for water demand as in most places in the world based on units per capita, and they assume some multiplier will occur forever. And they give whatever's left to nature. And that's not good enough anymore for South Florida. So the purpose of the scenarios is to generate some alternatives. For lack of a better term, I'm calling these deep scenarios. And the thing that's unique and hard about this for us is that instead of having 2 or 3 future points, 2010, 2020, 2040, because we're dealing with climatology and water, we're forced into having much narrower time steps. And so each of the climate simulations is being done with monthly time step data. Actually, it's being simulated on supercomputers with daily time step data. I just refuse to look at the daily stuff and told them, no, give me monthly. That's the most my brain can think to add to future scenarios. But effectively, we can run filters over those and look for periods of drought and periods of flood in the future. So it's a little bit bizarre in terms of a data source. But if you look at the raw data simulation, you basically get the weather forecast for July 18th in 2079, right? But what's important in there are the patterns actually of drought and flood, right? Probably I wouldn't bank on the weather forecast for 2079, but the distribution of extreme rainfall events, the distribution of drought is what you need to plan these water systems. And not the average doesn't matter so much, because on average you'll be fine. But in flood and in drought, you're going to have very, very severe problems. So the deep scenarios basically comes from that temporal depth, and then as well, we're basically at the point where we're embedding simulations into future scenarios that are fairly complicated themselves. And so this project has flooding and flood impact scenarios, for instance, a flood damage function. And it has drought and drought impacts, for instance, on agriculture. And it's got the aforementioned ecosystem services from the headwaters to tide. So part of the project was to get natural resource scientists working up in the center of Florida on little guppies in the streams, and those working on the mangroves at the coast, and figuring out basically, sorry for the typo there, but figuring out fish and fisheries, both from a commercial and recreational aspect. A couple of numbers I should mention to give you a sense of this. So there are, in southern Florida, 1 million recreational fishing boats. So recreation is an enormous economic activity. Some people have summarized it previously at $10 billion US per year. So the aggregate value of the ecosystem services in this area are enormous. And we can deal with those explicitly through fish and fisheries. So that's been one of our handles because those things are relatively well quantified. And the other part that we're doing in this project is carbon sequestration. because despite any national leadership on the issue, a lot of the states are actually imposing a carbon management bottom up. It probably won't happen in Florida in my lifetime, but you can always dream. So we're dreaming ahead in this and showing some examples of what carbon scenarios for Florida might look like. And by the way, I tell people in Florida all the time, Florida likes to feel that it's the victim of climate change because it has low elevation and is very subject to sea level rise. They're the #2 carbon emitter in the United States, which puts them very high in the planet. So people drive a lot in long distance with big vehicles. And so they're a major contributor to climate change. They're not just a victim. So I guess the reason for showing you this, even though it's preliminary, is kind of give you a sense of what we're struggling with and where we're going. So we're finding ourselves kind of as dealing with geodesign in a big data world. And that is a kind of context that has a lot to do with policy experimentation. So for example, we haven't done the stakeholder work on this study yet, but some of the questions I expect will emerge are, what if we require low impact development methods, either universally or in particular locations? What if we introduce carbon taxes? What if we put green infrastructure throughout the Everglades headwaters? Those kind of questions really are, at this scale, they're changed by rule, right? They're not changed by sketching. And so the sketch design tools that I helped work on when I was at ESRI are fundamentally mismatched with this task, right? So we need to have tools that give people a feeling of agency over changes by rule so that they can feel comfortable experimenting with broad scale policy changes. And that's kind of key to democratizing access to this kind of technology and data. And it's very different than sketching, but how it should be done is still open for reflection. So in that spirit, some kind of observations and on the current state of our practice and what we're thinking about and worrying about. Despite the name of my company, the majority of people do not come to me asking for geodesign services. And if they don't come to me, it's probably reflective of the broader world. So I've found it very useful to kind of consider geodesign as a set of methods that you bring people to, that they may not be asking for directly, but they are quite useful. And so the kind of framing that I hear very often is that people are looking for basically more robust planning solutions, and particularly relative to climate change, economic, and demographic uncertainty. And those three drivers are the majority of people that come in my door. And climate change is a huge challenge to most conventional disciplines that don't have this ability to organize with scenarios. So it's something we can bring to the table that's quite helpful. The second observation is basically that it's already been mentioned, but there's some support for geodesign concepts that's starting to emerge in software, but most of the tools basically require very significant effort to organize into viable workflows right now within a broader design and planning process. So right now we're at the point where education can get you through this. And if you have geodesign in your curriculum and in your education system, you can figure out how to get the tools to do what you need. So it's not that it's impossible with the current tools, it's just that it's not a staged workflow. You've got to kind of have a vision in mind of how you want the technology to work for you and bludgeon it into working for you, because by default it will not. And so it's really, that's where we are currently. The framing basically from the science point of view is often, environmental planning is often coming from a science perspective. And so I hear a lot about vulnerability assessments or impact assessments, and that's what I'm commissioned to do much of the time. And as Tom mentioned earlier, I find vulnerability a starting point, not a destination. It's great that I know that this species is vulnerable to sea level rise. It tells me absolutely nothing about what to do about it until I start to map it and I start to test policy alternatives. So in terms of conversations with clients, sure, we'll do the vulnerability assessment. And by the way, we'll add on strategic plans and designs, whether or not you ask us to, because it's just our nature, right? And similarly with impact assessment, there's kind of a notion out there that that the world is happening to us and that we're not agents in it. And so when I'm faced with people coming in the door with impact assessment questions, like, well, what's causing the impact? What design and policy changes might change those impacts? Let's not take those as a given. And that usually works because in reality, managers are facing those issues anyway. They just haven't had a construct to allow them to deal with them quantitatively. On the technical side, and this is in part for the technical people in the room, but in 2007, the main challenge I had when I showed up at ESRI was getting semantic sketching evaluation into GIS. So I wanted people to respect the designer's pen, in particular for GIS, to respect the designer's pen. And when the designer picked up a pen and drew a lake, I wanted the software to respond that it was a lake and not a polygon. So that's the semantic side. And I assumed that if we got the sketching part into the software, the analysis people would follow on and know what to do with the lake. I may have been overly optimistic on that front because I personally am still critical of the mainstream GIS software. There is an application called the Geodesign. What is the latest? I forget the release name, but anyway, they have an online GeoDesigner application that's much closer to the original vision. But effectively, the mainline GIS software tools still make it difficult to do routine impact assessment. So that's still a bit of a challenge. But from my point of view, the bigger challenge in 2014 is essentially how do we build an interoperable universe of geodesign tools? Not a single vendor tool set, but a set of tools that can encompass a whole variety of disciplines and interoperate, particularly for problems that are bigger and tougher than sketch planning, but actually including sketch planning. In this case, interoperability is one of the fundamental issues. And there have been a number of groups active in trying to do this, but it's been one of my big disappointments in web-based GIS that it's not really interoperable. So I don't know if you guys have the same feeling and experience, but you go to agency X and you get their map of water resources, and you go to agency Y and you get their map of development. And online, there's actually no way to combine those. So I feel worse off than in 1960 when I had primitive GIS. No, that was before I was born. But 1970 when we had very primitive GIS, but it was interoperable between disciplines. The web-based GIS is actually a lot of it very read-only and very sectoral. So despite the efforts of the Open Geographic Data Committee, we're basically still having trouble getting beyond the raw geodata level of interoperability. So we can more or less pass around points these days, but polygons are still tough, not to mention 3D polygons. And I guess more fundamentally, it's hard to transfer even basic common real-world representations across systems and between tools. So if you do something with terrain or you do something with water, those exist more or less everywhere. You'd think we would have software smart enough to recognize that interoperability, and we don't. And so that semantic level of interoperability is still very much missing. And that leads to the third problem, which it makes it nearly impossible to share models. And that's really, to me, the big challenge, because the kind of stuff we're just talking about involves many, many people contributing to many, many models. And we want to see an interoperable universe in which people can share that information digitally. And that's, until we get there, we won't really have geodesign, in my opinion. We'll have a lot of people trying to do it individually, but as a society, as groups of colleagues and professionals, we won't have real geodesign tools unless they're interoperable. So some routes forward conceptually. I think I've mentioned this, and I'll talk a little bit more in the course about this, but effectively you have 4 different starting points that people come to you with. You have science-only folks, to which basically my response is, let's think about stakeholders and address human action as choices, not only as stressors. I don't know if you have this kind of conceptual model in Europe, but in US science, the entire human side of the equation is usually what are called stressors, which is, as Tom has shown us, that's fair in a way, but it takes, again, this agency out of the equation. What are we doing that is a choice? In the US, that considers planning to be politics only, and so effectively when they come in the door, you have to start to get them to think about adding indicators and metrics and imposing some degree of order in using empiricism to solve problems. And it's not to say that the empirical answer is the only way of judging these, but unless you can have a conversation about geography and use indicators and metrics, well, you better hire somebody different than me, I'll say that, because I don't know what to do with just planning as straight out politics. If you're coming to it and you're interested in getting science information into a decision process, then I think we have a lot to talk about. A lot of these come from a context of a hard agency decision, and agencies tend to be very risk averse, and they're facing huge uncertainty, for example, climate change. That's actually a great opportunity for most of us in the room, because we have a reasonable set of answers and methods, not to climate change per se, but again, in terms of design methods, that we can take on those projects in a way that their internal staff is not prepared to. And then finally, I mentioned this already, there's a kind of formulaic, bureaucratic version of impact assessment. It's a sad thing to me. A lot of this legislation that we had in the United States that was very idealistic about citizen participation and governance and the use, requiring the generation of scenarios and alternatives and the use of impact statements in our country has been taken over by lawyers. And so you get environmental impact statements that are 8,000 pages and read by nobody, which is ridiculous, right? That's such a waste of those concepts. So to me, we need to reclaim those concepts and keep them democratic and keep them open. And in this day and age, that means putting them online, making those tools accessible to everybody. So the technical version of this that we're struggling with, but trying is basically, you know, we have to build useful tools to share scenarios through social media. And we are reformulating most of our work as online resources, software as service. So a lot of the stuff that we would traditionally do in desktop GIS, we're rejiggering to do as an impact model service. And to the extent that those are clonable and shareable and refinable by all of us, that seems to be a way forward that allows us to get broader reach out of the hard work of generating the impact model. I personally don't feel very proprietary about my impact model for sea turtles. If somebody can use it in Australia, I'm really happy. But all of that sharing of models needs to be worked out. And right now, there's both technical and political barriers. But effectively, we're working a lot on the technical barriers in the case where the sharing is easier. And the third element is a little bit techy, but effectively, the very invention of GIS was kind of a technical construct that made maps computable. And we now need maps to be computable, but we also need them to be online. And we need everybody's sketch, from napkin sketch to great design, and we need everybody's plan to be able to be evaluated by others. And that effectively means that we need to use the web for what it's really good for. And the application program interface paradigm, or API, is a little bit jargony, but effectively, all of you that have used a web browser know that if you have the ability to create technical objects that kind of link to a URL that's then interoperable, you basically can leverage the power of the web. And so in our work, we're designing scenario APIs and impact APIs that are exactly that are a URL that you can hit and get your plan evaluated for sea turtles, or a URL that represents and returns a scenario. So that's kind of the direction technically we're taking. So routes forward, the third thing, since I'm here in Europe, is basically to say we're looking actively for university and industry collaborators in geodesign. And we're particularly interested, obviously, in testing and extending some of the tools that we've developed in either studio or research settings. A lot of what I've learned is kind of that nice studio environment, interactive in person, where you watch people bash on tools and see what works and what doesn't work. Increasingly, we're doing a lot of it online as well. So we see what doesn't work and works remotely. I didn't really talk a lot about the technology we're using, but despite all my years at ESRI, we're actually largely using PostGIS and GeoDjango at this point. I've used both, and I would add a third. We're also, I'm on the consulting with Google on the Earth Engine project, which is a third web-based remote sensing and raster vector GIS platform. So I haven't picked a winner in that three-legged horse race, but we're trying them all. And since my colleague Bill Miller has continued to work on the ESRI geodesign solutions, I thought I would work on the open source side of things. So we've developed a series of extensions, and those of you that might be interested, look us up on GitHub. You can access some of these tools directly, and we can figure out basically how to grow this universe bottom up.